Assalamu alaikum. Today we'll be discussing Article 31.2 from Survey and Jute, and this is related to motional EMF. Uh, we have discussed in Faraday's law that by varying the magnetic field we can induce current and voltage in a loop which is placed near to the conducting loop. So in this case, when we'll be discussing motional EMF, in this case we will have a steady magnetic field, a uniform magnetic field, and we will move the conductor in that uniform magnetic field. So by moving the conductor we will induce current and voltage in the conductor. So here you can see that we have a conductor of a length L, and the magnetic field is it's going into the plane of the laptop. So the the placement of the conductor and the magnetic field, they are perpendicular to one another. Now we will move this conductor with velocity v from left to right, and in doing so we will the charges in the conductor, they will experience force when they are moving with velocity v. These charges will experience a magnetic force, and this magnetic force is given by Fp equals to q v cross v. The length of the conductor is perpendicular to both the magnetic field and the velocity with which the conductor is moving. Now under the under this effect of a magnetic force over here, both the electrons they move to the lower side of the conductor. So all the electrons, they will start accumulating at the lower side of the conductor, and the positive charge, they will start accumulating at the top of the conductor. So this process keeps on going, and as the charges, they are accumulating at top as well as at bottom, that is all the negatives at the bottom and all the positives at the top, they will establish an electric field within the conductor. So this field is from top to bottom. The direction of the field will be from top to bottom, that is from positive to negative, and the electric force will be in the upward direction. So now this keeps on going until a situation reaches where the electric force is equals to magnetic force. If you remember that we have already done this equation while we were studying velocity selector. So when we reach this scenario over here, when both the forces are equal to one another, then the charge accumulation stops, and we have QE equals to QVB. And now the equilibrium is attained between these two forces. Cancelling Q from both sides, we get E is equals to VB. Now, E produced in conductor is related to the potential difference, and we know that potential difference is delta V is equals to EL. Now, from equation 1, we can replace the value of E over here, and we'll get delta V equals to VBL. The potential difference is maintained between the ends of the conductor as long as the conductor continues to move through uniform magnetic field. So the moment we stop the movement of the conductor, the potential difference dies. So to maintain the potential difference across the conductor, we have to keep the conductor moving in the uniform magnetic field. And if in this case our conductor is moving from left to right, so we have suppose we have polarity from positive to negative. If we reverse the direction of the velocity, then the polarity of the potential will also reverse or will change. So the polarity depends upon the direction of the velocity. Now this is another case. In this case, we have a conducting circuit over here. This is R. So we have a conducting circuit over here. In this conducting circuit, we have these two rails. These two are the conducting rails. This is the conductor which we will move in the uniform magnetic field. The direction of the magnetic field is again going into the screen of the laptop, and we have connected a load over here, and that is resistance R. This is L, this side is L, and as we vary the width over here, so we will call this side to be X. So we are going to vary X, and L stays the same. So what we'll do is we will induce current in this circuit by moving this conductor on these conducting rails. And when we move this conductor on these conducting rails, the current will generate, and we will establish a current in this circuit over here. So uh, what we'll do is we'll move this conductor over here. So in doing so, we have to apply a force over here. So if we are applying the force in this direction, obviously the velocity will be in this direction, that is the conductor will move in this direction, and the magnetic field will act in the opposite direction. A magnetic force, sorry, so magnetic force will act in the opposite direction. So when we are doing this, we are basically inducing current in the circuit. The rate of change of magnetic flux through the loop and the corresponding induced motional EMF across moving bar are both proportional to the change in area of the loop, and we are changing the area of the loop by varying this distance x over here. So area in this case is L dot x, and we know that magnetic flux is BA, and from here we can replace the area with Lx, and now we have phi b is equals to Blx. Now differentiating both sides with respect to time, so I get d phi b over dt, which is equals to Bl into dx over dt. This is rate of change of displacement. So rate of change of displacement gives me velocity, and I can write it as Blv, which is equals to d phi b over dt. And we know that from Faraday's law that rate of change of magnetic flux is equals to induced EMF, and this induced EMF always opposes this change in flux. So we can write E equals to minus d phi by dt, which is equals to minus Blv. From here, by using Ohm's law, we know that I is equals to V over R, and in this case we have induced a voltage over here. So induced EMF divided by R, and the value of induced EMF is BLB. As I have taken the mod, so this negative sign goes away. Okay. Now we know from Newton's third law that every force has a pair, and that pair acts in the opposite direction. So if the magnetic field is magnetic force is acting from right to left, then there was an applied force which was acting from left to right and moving the conductor in the right direction. So we can write that the applied force is equals to ILB, which is equal to the magnetic force that we have. And we also know that power is equals to force into velocity. And here the force is the applied force, so I can replace this force with ILB, and now I have ILBV, and from the equation over here I can replace this I with BLV over R, which I'll do in the next step, that is replacing I, which is BLV over R, and putting it over here, and I'll get B square, I'll square V square over R, and this thing is equals to induced EMF square over R. So this is equals to the power. So this is all about motional EMF. I hope you will understand it.